Thank you everyone for joining us today. Again, we're back with our microgrid webinar series with Emerge Alliance. This is produced by Solar Power Events, but in lieu of some of our events being postponed to the fall, we want to bring you some great webinar content that you might see at some of our events, including North America Smart Energy Week taking place this September. So before we get started, I want to jump into just a few of the guidelines that we're going to run by as far as your participation in this webinar. In the Zoom program here, you'll see a chat area, so feel free to interact with the panelists, or if you have any questions, you can ask those in there or interact with other attendees. There's also a Q&A area. Ask questions in there. We will answer them throughout the webinar and a good chunk towards the end of the webinar when it concludes. Slides will, a webinar deck recording of this will be available and sent out to all attendees afterwards, probably within 24 to 48 hours. We also like to thank our sponsors, so Emeritas Technologies and Block Energy, for helping us put this together, as well as NorCal Controls Energy Solutions. Without their support, we wouldn't be able to do webinars like this, so it's excellent to see their support of the renewable energy industry. So without further ado, I'm going to hand it over to our host, Brian Patterson of Emerge Alliance.
Hey, thank you, Greg, and welcome everybody. I'm going to get right into it because we have a jam-packed agenda to get through, pass on a lot of information to you. We run this kind of as a town hall, so have a chock-a-block full lineup of guests and experts in the industry, and we'll just jump right into it. And if you're interested, you might want to jot down a name or a company, and you can contact them also directly. I want to remind everybody that we were inspired to do this by the coronavirus issue that's hit us. And I'm reminded now 4 times since the coronavirus outbreak has taken place, the power at my home office has been interrupted. And as such, each time I have to reset and lose the connectivity with my communications and so on and so forth. And it's just a kind of a warning, just like a canary in the coal mine, where they used to take a canary in to see if there was any poisonous gas in the mine being released so they could get out in time. But there's a lot of things that are hitting, potentially can hit the grid and power system. So that's really what has inspired us to talk about resiliency, probably as a fundamental aspect of what we're talking about. Whenever we talk about resiliency, we always get down to talking about microgrids and other topologies that can help the grid. Certainly what we're all trying to avoid is the inevitable outcome, if we're not careful, that we might be sitting in the dark someday without communications, and that would be just horrific. As we've kind of experienced, just being physically distanced from each other is already tough to do. We have some really great experts today, and the subject is direct current DC. So leading off the headline list here is Dave Geary from Comcast. And Dave, I call him Dr. DC because he is and has always been, for me, the expert when it comes to questions about DC and how to do things. But another person that has formed, in fact, the next 3 guests have all formed companies that are expert in the DC area. And I don't mean District of Columbia, I mean direct current. And the first off would be Ron Gdovic, who runs a company called Windstax Energy. And you're going to hear from him about how he's implementing some DC technology in his systems. Andy Peck from Peck-LUMAnext is also going to talk about what his relatively new company is doing and some exciting things there. And Paul Savage, who's actually a co-founder with me of the Emerge and Chairman Emeritus and does work with Nextek Power Systems, is also on, and he's carrying his Emerge credentials. So he is always involved in a lot of different things. So we're going to hear from all those guys. But we're going to start out with the basics. And for a lot of people, this is the challenge. DC is not as well understood and practiced and so on as AC, the kind of power mode that we've been dealing with the last 100 years or so. So we're going to jump in a little bit with the details. And I'm going to ask, as I said, Dave Geary principally to respond to some of my questions. But Dave, maybe you could explain to everybody the fundamental difference between AC and DC. I know there's a lot of experts here that'll say we already know that, but some people don't.
Well, I think this is as deep as we're going to go on the engineering side of things, but we wanted to start at the basics. What's the difference? What is DC compared to AC? Well, AC alternates, obviously. And in the United States, that sine wave is a full cycle that operates 60 cycles a second in the United States, where it's 50 hertz and 50 cycles a second in Europe and other places.
And that sine wave is actually the voltage, right? The voltage is changing?
That is the voltage changing, but the current, as it goes through loads, follows that same sine wave, either leading or lagging, depending on what type of load it is. So again, that's the engineering going to speak for today. And,
okay. So we can't help but notice that AC has been the predominant mode of electricity for nearly 100 years. And why is that? What are the underlying reasons for AC to be so dominant?
Well, there's a few examples in these coming slides, but the whole electric grid started as DC, but very quickly turned to AC with Tesla's invention of the AC power and AC voltage. One big reason was the ability to develop transformers and change the voltage to raise it and lower it depending on how it's moving through the transmission and distribution system.
Well, why is it so important to get the voltage to go up or down?
Well, higher voltage, less current and less copper. So the idea was to get it as high as possible so the conductors that bring the power to us can be sized accordingly. And in doing that, going to high voltage allows you to go to the lower and smaller conductor size. And as it gets closer to the load in our house, obviously you see the wires change in size to be accommodating for the lower voltages.
Okay, so if we kind of ran 100 volts power across town, you'd have some issues, wouldn't you?
That is for sure.
Okay. What about what else has caused all this ruckus about AC?
Yeah, the other big benefit to starting with AC power at the beginning was the invention of the motor too. Again, DC powered motors didn't exist back then, and so they were all basically AC, and it allowed to manufacture varying sizes of horsepowers and motors, and that's what actually spawned the industrial revolution as a result.
And I guess actually a motor in reverse, so to speak, if you turn the spindle on the motor using a steam turbine or something, you can actually get an output of electricity, right?
Exactly. So the motor is a motor if it's powering a load, and it's a generator if it's powering electricity back into the system.
Great. Okay, so we all, in fact, there's a movie out now, right, about the current war and so on and so forth.
That's exactly right. Yeah.
Yeah. So I guess one of the things that I would say is that, a lot of people get confused as whose side everybody was on, Tesla and Westinghouse and Edison and all. But the war was won for those underlying reasons that you just spoke of, right?
That's exactly right. Thomas Edison started the dance, so to speak, and he invented the light bulb. He invented the load. So once he had the light bulb, he had to develop a system to feed the light bulb. Sort of similar to what we're starting to go through again these days, where we're starting to see more and more DC loads. So the systems are gravitating towards being sources for them. So we started with DC with Thomas Edison. Thomas Edison was probably a great inventor, but he was not really the friendliest guy. So people like Nikola Tesla, who worked for him for a short while, like other people, basically had some ideas that he tried to convince Thomas Edison of, and Thomas Edison wouldn't think anything of it. So Tesla went out on his own and ended up partnering up with Westinghouse and developing the whole AC infrastructure that we see today. And speaking of what we see today, look to the right there. You look back at when the telephone was invented and what we're doing today and what we have in our hands today with our iPhones and so forth. And one thing we sort of point to is The electrical infrastructure, although it has some new and exciting type of devices and systems, it's still the basic infrastructure of generation, transmission, distribution, all the way down to the load. So it really hasn't changed much in the 100+ years that it's been in existence.
Yeah. And that S curve over there on the right, as you point out, is kind of flattened out a lot. I guess that's kind of where we are, is on the flat of that curve. And usually what happens with technologies, as new technologies come along and start new S curves. So I guess the big question is, what happens to this curve? What does it get replaced by? And we're going to ask that question later on. So stay tuned, if you will, folks. So now there's a lot more talk about DC today, for sure. What's the reason for that? And when did all that start?
Yeah, why the change? Well, it's basically because of the DC transistor, the power electronics that you'll see coming up. But was the transistor, the semiconductors that, in fact, when I first saw this, I was surprised that it happened back in 1948. But that was the beginning. You know, we started to see the semiconductor industry, I guess, come alive. And as you'll see in the coming slides, that as it's developed, it's bringing us back to this DC world.
Great. And there's a couple of other things going on, right? We see a lot more of those blue flat panel stuff hanging around. So what's with that?
Well, again, the big interest in renewable energy is I think everybody's interest, and the fact that renewable energy is basically powered by DC generators, PV panels, and stored in batteries as DC power. So again, as these technologies develop and they're more DC centric, we're finding that, again, the path back to a whole complete DC infrastructure is making its way and making it a reality. The other thing, like I just said, was the energy storage. Batteries are inherently DC powered. You know, I work for Comcast, and we have basically a 48-volt critical infrastructure that we live on. It's powered by lead acid batteries, and that concept really goes back to the beginning of the telecom industry with Ma Bell and their 48-volt DC infrastructure.
Now, and today there's a lot of discussion about lithium-ion type batteries, but I guess there are other types of batteries. So when I think about it, I think about storage as being the equivalent of the storage that you have in a computer for data. You know, you have some up by the processor, up by the processor chip, you know, the cache. You have some in maybe a hard drive or a thumb drive, and then you have the cloud. So there's lots of places you can put storage, right?
Exactly. And that's really the next wave of what we're going to see. We've had a good, gear up of PV or solar installations, and they're becoming more and more. But now more and more we're seeing is the solar installations coupled with batteries to supplement and flatten out the peaks and valleys of a typical solar operation, and wind.
So you mentioned power electronics before. What does that mean?
Power electronics. Well, you're seeing some of the examples here. The IGBT. Then we've actually started with, I think, the MOSFET. Again, I guess more engineering speak, but the IGBTs were faster and smaller and more cost effective. The next generation we're seeing is silicon carbide, and then finally GaN, that's starting to make its way to the market. These are new generation power electronics that make us have the ability to have smaller devices and do power conversion a lot easier, more efficient, and they're finding their way, as you can see, into not only appliances, but if you go to the next slide, I think we start getting into the electric vehicle market and other
Before I leave this, you had promised that you weren't going to get too technical, and I heard you reel off about 5 acronyms there. But I wanted to sort of point out to folks that the progression of these electronics, this power electronics, very similar to the progression that we saw in semiconductors used in computers, right? So you get this Moore's law kind of exponential improvements, and so we may not be done with this, right? It's going to continue on and get better and better.
That's a great point. Really, the power electronics started in the computer industry, and the transistors that was their first home. But as we're seeing, everything that's happened in that industry and the developing of the higher voltage DC is pointing towards these new use cases and the ability to use these same type of devices in different ways.
Right. So when people ask, they often ask me, well, what difference does power electronics make, and what does it affect? I think you might agree, Dave, that just about everything is being affected by power electronics, right?
Yeah, just a few years ago, I think they showed on that one slide, they basically, the word was that 80% of all power goes through some type of power supply and it ends up being DC centric at the load anyway.
Yeah,
that's absolutely just increasing. Yes.
Absolutely amazing. Just like the transistor itself was in the beginning. Now, one of the other things that people always talk about when they compare AC and DC is the whole notion of what people call synchronization, right? Exactly. And I guess it makes a difference whether it's single phase or multi-phase and all that kind of stuff. Can you talk us a little bit through that, what's involved there?
You've always done a good job with this one, Brian, but I'll take it as the law. But if you refer back to that sine wave that we showed at the beginning of what is AC versus DC, if you look at that AC sine wave and picture that there's not just one of those for voltage, there's typically in our system 3 of those that operate together to get us 3. And that voltage has to match if you're putting other loads together and other sources together. So it's the constant adjustment of voltage and frequency that brings sources together so they can work together to feed loads. That's not trivial. But as we start seeing these distributed energy infrastructure develop, and those sine waves have to be resynced over and over again at different points within the system, we're starting to find that eliminating this complexity of synchronization is a good thing, and that's what DC power gives us.
Yeah, and we just recently had some folks on in our last webinar talking about coupling, AC coupling, DC coupling, and they constantly referred to the AC side as its main challenge is the synchronization of multiple sources coming onto the same bus.
Agreed.
So there's that has to do with power conversion or integration, but the loads are changing significantly. And I think you mentioned this right up front, that so many things are electronic. And I don't think people realize that. I know when I first got involved in the business, 20 years ago, they always talk about toasters and lights, incandescent lights, as being the major loads in electricity. Today, I think most of what I hear and understand is that the single biggest use of electricity now is in semiconductors, mostly for the data industry. Data centers, cell phones, you name it, everything that we use to communicate with.
That's correct. And that's actually where this whole idea of this higher voltage DC was born out of back in 2006. A group of us got together and looked at the telecom industry, looking at the 48 volt infrastructure that they've had for years. It has been so reliable and efficient. We said, why can't we do that in data centers? Well, at 48 volts, it just doesn't play as low voltage, high current and megawatt data centers. And as you see by this chart, these data centers and cloud computing are going to, if they're not already here, the 3rd largest consumer of power in the world. So that's where it all started, is looking at a higher voltage DC. So we had folks like Intel and HP and Sun Microsystems at the time, and we did a proof of concept project. And we said, let's try a higher voltage DC. And as it turned out, Intel was already looking at that. They said, well, if you're going to do a higher voltage DC, just give us 380 volts DC. We sort of scratched our head, and that's how we learned the whole power supply story, that the sweet spot of power supply and converting AC to DC that every computer does ends up being around 380 volt DC within that power supply.
I wanted to point out on this slide that you had that you in a sense passed over the killer app here, which is the electric vehicle, right? As time goes on, charging electric vehicles as sort of like a grown-up version of your cell phone is going to get to be a challenge for the grid.
Yeah, and as we're looking at the high rate chargers that are starting to hit the market now that we know we need to build out the whole charging infrastructure, it ends up being about a 380, 400 volt DC application.
And like I said before, lot of people would say that, you know, AC was the predominant mode of power for powering electric things. But actually, that conversion has been made. Now, people don't necessarily realize that we still use AC to distribute and transmit most of the electric power, but its actual use is almost predominantly in DC because of the use of electronics. But that's now permeating everything, you know, EV transportation, the Internet of Things, of course, which is all the ICT equipment or information and communication stuff here. But there's more to come, right? The electroactive environments, I see, you know, mixed virtual reality with mixed enhanced reality. And then, of course, you have the old standbys of population growth, maybe not as much here in the US as other places in the world, but the population is expected to continue to grow around the world. And in population growth is a kind of a double whammy there, because as we get better and better with our communications and sharing of technologies, developing economies are moving at a much more rapid rate than they've ever moved before. And in a developed economy, there's a greater use of energy in general, but electricity in specifically. So there's a lot more electricity that has to be generated and used. And of course, the challenge there is, can you do that without damaging the environment at the end of the day, and do it at a reasonable cost?
Right. Think about what we're going through today with the COVID virus. What's that going to do as far as changing what some of these loads are going to look like down the road? I'm sure ventilation systems are going to be upsized and their changes are going to be increased. And if we could figure out if really the ultraviolet light is a source of disinfectant, just think of what that's going to do within our everyday life. So things are developing as we speak, even in regard to what we're going through altogether. And my contention that DC power is very friendly to those type of
there's a lot of similes and metaphors that you can draw between what's going on in the health and you know, I guess you'd call it the social world, as what is also going on and being challenged in the technical world. We'll get into that as we talk a little bit more about microgrids and the whole idea of social distancing, which is a social way of making sure disease doesn't spread or viruses don't spread. But I think we have something similar that we want to do with electric power as well. You mentioned about voltages. Now, when people start talking about voltages, you can talk about, you know, semiconductors at around a volt or so, and then you get to 5 volts, which is what most consumers start to understand when they charge a cell phone and things. 5 volts, and then there's you know, 12 volts, 9 volts, 12 volts, 24. But those are all voltages that are actually just being utilized. There's typically, as in the AC system, you want a good operating voltage that you can kind of peel off all these other voltages from. So would you review one more time how you got to the 380 that you are espousing?
Once again, it was the load that sort of dictated, and the legacy infrastructure that was built using AC power. Well, if that AC power is being converted to DC power at the load itself, then the first thing we wanted to do was satisfy the load, and that ended up being 380 volt DC sort of sweet spot. And that's what you sort of see here. We have all these other different voltages that is going to be my contention that are going to develop over time, and every device and every application will develop its own sweet spot voltage. But the first phase is to come up with a standard that was endorsed by some of these organizations that you see here, and that's what we did. But we're already seeing different higher voltages, taking 380 volts and doubling it for larger scale microgrids. Right. And just to point out, it's not high voltage DC, it's just higher voltage DC. We don't get to high voltage DC until we go above 1500 or 2000 volts to really categorize it as high voltage DC.
And then, of course, ultra high voltage DC, which you'd use in transmission, in fact, is being used quite extensively now in transmission. Yep. Some of the new networks that for transmission networks where you have remotely located distributed energy, like solar farms and things like that, to move that electricity more and more being used as the ultra high voltage DC as well, right?
Exactly.
Now, and that doesn't really square up with what we've been told for most of our lifetimes, is that DC can't go very far, but that kind of gets back to that whole voltage thing, right? That as long as you get the voltage up. right?
That's a great point. When we first started throwing out the concept of the higher voltage DC, the questions already came back, and you'll see the next one with the slide following this. But what about voltage drop? Don't you need to have real high or large conductors? And but actually, voltage drop is less in higher voltage in a DC in general, and you go to the higher voltage DC, and it becomes even lesser. But then the next question, safety.
I just saw a question come in, which I think we want to inject right into this discussion, because is 100 volts of AC the same as 100 volts, what we call 100 volts of AC, the same as 100 volts of DC? There's something about root mean square in there, isn't it? You got to divide by like 0.7 or something.
That's correct, because that's another sort of misconception. If you look at that sine wave that we saw at the beginning, that 120 volt sine wave is actually an average of the area under that sine wave, under the curve. And as we get noise on the line and those sine waves become distorted, the root mean square has to be calculated to actually calculate the area under that curve, instead of just arbitrarily calling it 120 volts. So actually the peak of that voltage is a 120 times the square root of 2, where the DC voltage is strictly running at a constant 120 volts. So it's the AC voltage is actually higher on the peak voltage than the DC voltage is running continuously.
Yeah, I always divide by 0.707, and that's because I grew up flying a 707 jet. It's easier to remember than the square root of whatever you said. Yeah, but that also means that peak voltages on the AC side are higher than the actual label voltage, right?
That's correct, and that's there's been already studies done on the high voltage DC and comparing it to the AC as far as safety goes. Not to mention just the idea of doing things differently, like grounding and solid state protection devices and so forth. That DC is inherently safer because of the fact that the AC is a fibrillation source and actually stops your heart, where DC actually doesn't do that. So in fact, I think all the defibrillators that they carry around are DC charges that they hit you with to try and get your heart started again.
Right.
So again, there's been studies done to show that DC is safer, and some of these use cases and voltages as compared to where they are in the system are being studied even more and more to prove out the fact that there's ways to make this DC infrastructures ultimately safer than AC power.
And I did put on the slide here a link that people can go to and get more information about the safety, because we could actually do a whole webinar just on safety of electricity. And we don't belittle the fact that any high voltage electricity is going to be dangerous, whether it's AC or DC. It's just a different threshold. So you're going to get into trouble faster in AC than you are in DC typically. But again, either can be dangerous, either can kill you at the right voltage and right current for the right period of time. So make sure you understand, if you're going to be working with systems, whether they're AC or DC, that you fully understand the safety implications of what you're doing.
The good engineering is a must to guard against safety. So that's for sure. So
we talked about some neat kind of features of DC, but if our theme really these days is about resilience, how do you use DC to get more resilience in the system?
Well, the quick answer to that is you're starting to see the interest in microgrids and distributed energy resources, bringing the sources closer to the loads. I submit that, if I could have a small generator and battery in my house and not have to rely on the electric grid, it makes me more resilient, because I have control over it, and I can take care of it. And when I need it, I can use it the way I see fit. So that's really the big cases, is the actual distributed energy resources and microgrid capabilities, and coupling things like solar power and energy storage together where we need them. That really makes or increases our resiliency.
Yeah, and you can use fast acting switches to decouple, and this is where I drew the analogy before about social distancing. So one of the remedies to problems on a grid, whether it's an AC or DC grid, is to decouple, and you can do that extremely quickly and not have to resynchronize when you want to go back on the grid or back connected to a grid. So I guess that's pretty important, particularly if we start networking microgrids together, which we'll talk about in a second here.
Exactly.
The other thing that most people forget is they always look at when you get into discussion on microgrids, it's a we versus they, kind of, is it the big grid or the microgrid? But actually microgrids used properly and designed properly can actually support the main grid in a lot of ways with, as you mentioned here in the slide, things like demand response and peak shaving and, clipping the extra generation that can't be used right away and storing it and doing VAR support and so on. So
certainly we'll be working together for a long, long.
Yeah, so there's a lot of reasons. And of course, a lot of the I won't go through the detail of this slide with you, Dave, because you've already, I think, mentioned most of these. The idea of how do you
of these benefits? So absolutely.
Yeah. How do you get to what's the magic of getting to lower total cost of ownership? That's a combination of the stacked value proposition.
Yeah, and the ability to be modular and scalable, I think, is one of the big benefits of the infrastructures that are developing today. Mm-hmm. Instead of going out there and putting in a 1 megawatt generator and bring everything online that you think you might need in the future, you can actually start building some of these systems that grow as you need to grow and are modular as we put these sources together to feed the loads as they come to fruition.
The other thing is putting the value on resiliency. I think if you did a stripped down version and didn't care if the power goes out and you sit in the dark, as I mentioned before, for long periods of time, perhaps, then you don't worry about resiliency, and you can probably squeak some more cost out of a system and say that a system that you're speaking about here might be more expensive. But if you factor in the resiliency and the total cost of loss of power for long periods of time, or even short periods of time, power quality and all those issues, that total cost of ownership, if you really do an apples and apples comparison, can get to be very competitive, I suppose.
I agree. And we're just getting started. And again, that's some of the folks that are following to give their case studies can probably give more insight into that. So absolutely.
Yeah, as always, it all comes down to what do you value, Right. I never thought I'd be paying $600 or $700 for a phone, but I regularly carry one in my pocket, and I don't seem to worry too much that it cost me about 10 times what a phone did about 20 years ago or so. In any case, there are different applications for microgrids. I know, Dave, you've specialized in data centers, telecom stuff with Comcast and others. Buildings in general, though, have been the early targets for microgrids, the so-called behind-the-meter applications. And there's reasons for that, right? There are benefits that it can accrue to all those different applications.
New technologies start with the low-hanging fruit, and that's exactly what's happening over the beginning of all this new higher voltage technology. But very quickly, like I said, it's moving outside of all these applications and finding their way into more use cases that become sweet spots of doing different things at different voltages.
I think one of the important things here to understand is that the use case is a determining factor in the value of the microgrid or any power system. So that it's important to understand what the use case is going to bring and what kind of a microgrid you want to put around it. So, I mean, it sounds like a great rosy picture for DC, but, why isn't everything DC today? It's just not, we're still using AC, or at least feeding the equipment with AC, and I guess everything has to convert it to DC. But so what are some of the challenges there that you're looking at, Dave?
Well, the first part was standardizing on voltages. 380 became a standard that actually now allows some of the appliance manufacturers to go into production and say, yes, we provide a 380 volt DC model. Standards have been an issue, but all the standards bodies, even up to now, are pretty much gone through and developed the 380 volt version of all of their standards. And then it becomes, the change itself. Change means change. So there are actually, we've have done tests where we've actually just plugged 380 volts into, electronic ballast for fixtures. They work fine. We've actually plugged 380 volts into appliances, and they work fine. Just because, again, these appliances and these devices have power supplies in them that take AC, convert it to DC, and if 380 volts is, again, the sweet spot, it works just fine. So it's making these changes, going back and trying to get the appliances and other things listed to take both AC and DC, We already have all the computer manufacturers that offer or can offer 380 volt DC versions of their power supplies and all of their computers. So things are happening over time. So, but it's not going to happen overnight. You're right.
Yeah, and I guess the last item there, education, training, market awareness, is what this webinar is all about, and all the things that are done at the trade show, the SPI North American Smart Energy Show coming up in September, and we'll talk a little bit about that towards the end here. But you know, the DC side isn't done yet, right? There's additional things happening with power electronics and circuit protection and control that are going to continue to change the turf here, right?
That's exactly right. In fact, you know, one of the, not a problem, but one of the things we've had to do in developing a whole DC-centric infrastructure, we're making it look a lot like AC because that's what we're used to. As we develop these systems and deploy them and test them, and actually we're starting to see new things come to market, like an electronic circuit breaker that basically eliminates arc flash exposure because of how fast it is. That's one example. If you go to the next slide real quick.
I was going to point out, I read the fine print there on that. It said that there was 3,000 on-offs, if you will, per second versus 60 that you get in an AC zero crossing, right?
There you go.
So that if I understand it right, that means 3,000 times a second you can interrupt that current, right?
Yep, in microseconds, and that's what that takes care of the arc flash exposure.
I mean, there's not enough electricity to even shock you if you at 1/3000th of the number of joules going through the wire is probably not even going to shock you.
This is actually another example of that. This is a digital electricity where they send DC power out in pulses similar to digital communication at 6,000 pulses per second, and sample each one, and that they do the same thing electronically that the breaker does, and is able to open the circuit and become touch safe as you distribute the higher voltage DC.
Yeah, I am definitely hearing that term touch safe coming up more and more. I was talking to one of the utilities who happens to be a sponsor, by the way, of this program, talk about touch safe, and they're talking touch safe at the higher voltages, which is just incredible to me that you could make something that you could touch that's in the hundreds or even low thousands of volts. That's kind of interesting. Well, Dave, thanks for all of that. And feel free to continue to comment as we get these experts, actually, not only experts, but true practitioners of the technology. Once again, I want to mention that we have Ron Gdovic, who is the CEO of Windstax and Windstax Energy. They do a lot of work, and as their name implies, there's some wind involved, but there's also the important part is energy. They do complete systems and microgrids and so on. We also have Andy Peck, who's from LUMANext, and as I mentioned, they're doing some interesting stuff behind the meter as well. And I think I already mentioned Paul Savage, who will talk about some of the applications that he's familiar with. So I'm going to turn it over to Ron a little bit and have him describe for us, you know, on the basis of everything that Dave talked about, you put together a company that's doing some amazing things. What are you doing?
Well, thank you, Brian. And yes, David, you're a tough act to follow. But yes, Windstax Energy, we've been in business for going on, 10 years now. And today we actually manufacture the largest vertical axis wind turbine in the United States. Here's an image of 8 of our 60-foot wind turbines. A lot of advantages to vertical wind turbines. As you can see here, they're closer to the ground. They can be mounted close together. And as you can see, this is a commercial/residential area. So a lot of benefits to that design. But that's a neat product that we make, but really the magic is in our microgrid systems. All of our systems are hybrid wind, solar capable, and also other alternative forms of energy using a battery for storage. So I'll give you a quick example. When we started out, we actually started in the residential market, but how important the kind of behind the meter world can be in distributed energy resources. As David mentioned, we have a residential couple who are an elderly couple, and they need CPAPs to to breathe. So they have one of our smaller 20-foot wind turbines, a limited amount of solar and battery storage. So this is a system that we installed and designed that gives them a full 8 hours of battery backup should the utility be lost. And this has happened over the past 5 years, a number of occasions where our systems have helped them run their CPAPs through the night without utility power. But scaling up to that, the commercial projects that we do now are in the megawatt range. So the one I just showed you earlier was for a trucking and logistics company south of Cleveland. And our philosophy has been prosumption, which is what we trademark as what's called zero first. So the idea is to generate, store, and consume as much renewable energy as possible on site, relying on the grid as a backup and sending power back to the grid that's in excess of demand on the site. So what this graph shows is throughout a period of a day, throughout the evening, before sunup, we may be using grid power. Then as the sun kicks on, you can see the solar generation come up, and that not only charges the battery, it runs the loads at the facility, and as the sun goes down later in the day, you go into this self-consumption model. So this facility in Cleveland that I had mentioned uses 500,000 watts of solar panels on the roof, and they're actually in an east to west configuration, which we have found over the years through experience is far better for our topology of battery storage, because you want a nice long charge throughout the day. So that works well. In fact, this building was designed really from the get-go to take advantage of a distributed energy resource, this microgrid. So this building is the eave is actually facing south, and the panels are east to west. To further take advantage of this design, all of this facility is powered by a DC distribution bus. So we are running 380 volt DC all the way to the fixtures in this facility. This is an image of our battery. This is a 1 megawatt hour lithium ion battery that is really the heart of the system. So we are generating wind and solar in the 900 to 1,000 volt range and storing it and then stepping it down to 380 volt DC. So this customer, in here you can see the high bay lighting, and office fixtures are running on DC as well, step down further to 24 volt DC, which I'm sure you'll hear more about shortly. So yeah, so this is a unique philosophy, but it's very important to this company to be resilient and be able to island. In other words, they need to be able to function long-term if the utility grid is lost. And theoretically, because we also have a backup generator on this entire facility, this facility can run on renewable energy theoretically as long as it wishes to. So, Brian, with that, I know I'm a little past 5 minutes. I don't want to take too much time.
Well, I did want to point out that I don't know if it's permissible, but I think most people recognize the roll-up doors on this facility, that it might be a logistics terminal of some type. But it's interesting during the last couple of months now, logistics and the ability for logistics systems to stay up during any kind of a crisis was absolutely paramount. And it almost didn't matter whether it's trucking, passenger vehicle kind of transport to bring my lunch over from Chick-fil-A, or the air transport systems, the airports and so on. So logistics in the case of resilience, in a bigger picture of resilience for society is critical. And so it's interesting that, so one of the more important applications that you've worked on here is logistics oriented. So congratulations on that, Ron.
No,
And I know you guys do a lot of other things, and
Mhm.
we'll have to try to get you back sometime to talk about some of the other applications that you're involved in. But I thought this would be the most interesting one to people because of the dependence that we have in the national emergencies on logistics. So next, I'm going to turn it over for a couple of minutes here for Andy. Andrew Peck, who operates out in Pittsburgh as well, right? That sounds like a real hub for these kind of activities.
Between New Jersey and Pittsburgh, both.
Yeah, okay, New Jersey and Pittsburgh. But in any case,
tell us. We have the best of Westinghouse and Edison.
There you go.
Ah, there you go.
Tell us what you're up to with DC in your future.
So I'm going to make it a 2-minute elevator speech today to give everybody else some more time. But basically, we work in low voltage DC nanogrids, so 48 volt. We invented a electronic switch for 48 volts, which is key in the safety of working with direct current. And we've installed over 1,000 of these systems around the country. And we're kind of evolving now more into chip to grid technology, where we believe that the DC should be running from the grid, from a microgrid straight through into the building to all the loads of a building. This first slide shows that the great advantage of, actually an intangible advantage for the circular economy, where you could eliminate drivers and a lot of these components when you switch from AC to DC. And the end result is getting rid of those drivers, which ultimately end up in a dump. And you could ultimately, eliminate some of these terrible landfills that we have all around the world.
This is kind of one of the hidden things that nobody talks about, is the fact that if you feed the AC directly from the grid into devices, they have to have these conversion modules and things, whether they're the wall warts that we're used to. I got probably a few totes full of these things that get obsolete pretty quickly.
There's another very large benefit that people are not aware of, and it's the elimination of flickering. So if you have LED lights in your building and you're running them on AC with a driver, you could most likely have the flickering effect, which could cause headaches, migraines, and you wouldn't even know that your headache is coming as a result of really poor lighting from generic LED lighting. So having a DC infrastructure for a building and running your DC components on DC makes all the difference in the world. One of the things I want to talk real briefly about is the Patterson project. And we believe that to get direct current to be a accepted primary energy source for a building and for a community, you have to reach first into the community. So a large part of what we're doing today is in Patterson, New Jersey, and working with the school system, working with the political system, the mayor's office, and with community groups about the benefits of redoing an infrastructure, redoing buildings, and educating the population. It creates jobs, it creates internships, it creates a smart infrastructure. There's so many benefits to the inner city especially, and one of our goals in DC is to kind of end the energy divide and try to end the education divide in this country. And at this time in our country, what a great purpose to have. And so you're not going to think DC to end a divide. Well, and the next slide will show you that direct current creates jobs, it creates opportunity, and it creates opportunity for young students in inner cities to learn a new trade. And that new trade basically has to do with smart city, IoT, direct current, and a whole new system. One last thing is, on this Patterson project, a huge component of this Patterson project is to create the jobs in Patterson to manufacture those products, to get the students, the high school students, to become interns to install DC lighting because it's safe. And it gives them the pride of doing it and interest in learning about these new technologies.
That's great, Andy. I'm going to turn it over to Paul Savage to talk about some of the things that he's been involved in more recently, and one of those is the Regis Gastown project.
Thank you, Brian. Yeah, Regis is one of the 8 or so brands of the IWG group, which is a public company in the UK that has co-working spaces all over the world. Their most famous ones in North America are Regis and Spaces. They're in all the great metro locations. And this is an interior of their Gastown location. That's a historic district in Vancouver. We have been happy through their owner's rep to show them how they can save money, not just on the installation, but the operation of these low voltage lighting systems. I think you can see here that we've got a pretty good variety of luminaire types, which is important for blue chip customers like Regis. And we've now been able to find complete DC systems with fixture packages 70 deep to provide really a complete palette to these major customers. If you go to the next page, there you go. Just some of the benefits, and Dave and Andy and Ron have all touched on this a little. But I can tell you 5 or 6 years ago, I would have been discussing how you get paid back a premium by putting in these advanced controls-rich LED lighting systems in a building. But that is no longer true. We are less expensive on day one because of the lower cost of installation of our system. That's the installed cost of the fixture, the power to the lighting, and from the lighting panel, as well as the controls. And you can see here a little analysis of 3 of the Regis projects that Nextek has done in Vancouver. That's the photograph, Toronto, and Chicago. If you're next time you're in Chicago, if you're looking for a place to operate from on a temporary basis, the River North neighborhood there is the location of the largest Regis property, or I think it's a Spaces property in Chicago.
And you kind of, yeah, go ahead, Paul.
I was just going to point out that I show some metrics there about the cost of the power versus the cost of control for these systems. And for people familiar with the installed cost of lighting and control, you can see that those are very attractive for a system of this kind with sophisticated controls. Go ahead.
Great. And continue to comment, but we're running out the clock here. So I'm gonna jump into just a couple more things that we want to touch on. And then I want to ask the audience a question through the polling technique. But we're talking about this kind of migration or potential migration from the current electricity grid to something that maybe resembles more like an internet, where there is an integration of microgrids into the grid in a variety of different ways that will lead to a sort of a grid of grids concept and give us a lot more functionality and more of the networking effect that we enjoy in the information systems. And so you saw this chart earlier where the S-curve ended up at the top here with AC being fully implemented by middle of the last century and continue to grow, but not change very much. And most people think we're at this point of change, whether it's going to go and stay the same and just be maintained in the way that people talk about, faster disconnects and smart meters and things like that, or is it going to go into a more of a DC future in this what we're looking at as a grid of grids? And so we're not talking about just one microgrid that might be in a building, a home, or what have you, but then networking those in local neighborhoods and in communities bringing in additional resources at the community level, and a full integration, past substations back into the existing utility grid. And of course, this is in parallel, and a lot of this will take place in new developments and new communities where it's easier with a blank slate to start this way. But you'll notice in this diagram that this particular company, Emera Technologies, which is a division of the Emera, the utility that runs up and down the East Coast with territories, that most of the grid is DC in between, in the neighborhood, at the building level, and so on. Of course, if your building has AC equipment and so on, you need to put the inverter here, but it's not a synchronized to the grid inverter. It's just an inverter to run AC appliances, and the same thing back connecting to the grid. So those are both bi-directional kind of connections that you can do with traditional inverter techniques and so on. But the bulk of the grid here in the mid section is DC to avoid all the synchronization, where you have this kind of peer-to-peer connectivity and sharing of resources. And the model here is even that the utility supplies the local distributed resources and the integration capability. And of course, then coupling communities together really gives you a whole other dimension of resiliency. Some people call it the archipelago effect, and some people call it the networking effect, but suffice it to say is that more and more people are looking at the topology that's more typical of the internet, and why most people believe the internet to be so resilient. So I want to ask a question. So I'm going to ask the folks to look at their polling thing. I'm going to send out, I'm going to launch the polling and send it out to everybody so you can respond. And I would like to know, or we would like to know, what do you think the grid will end up being? Will it stay centralized the way it is? Will it kind of transform over to an entirely decentralized system, or will it be some kind of a hybrid? That's the question number one there. And if you'd respond to that, we'll report back to you what everybody thinks. And then the other one is about AC and DC. Do we think it's going to stay primarily AC? Is it going to transform to primarily DC? You heard a lot of good things about DC. Or is it, again, going to be a hybrid? Is it likely to be a hybrid over time? So we'll wait for people to do that. While doing that, some people have asked some questions. I want to go back over just the thing about frequency or zero crossings. The AC line currents today are either 50 or 60 hertz typically around the world. There's some others, but those are the predominant ones, which means that you go through a zero voltage, 60 times or 50 times a second, right? The fast switching, I think Dave mentioned digital electricity. The systems, at least that I know of, are operating in the hundreds of cycles. So they're, I think, in the 300 to 500 or 600 cycles, roughly 10 times, let's say, what zero interrupt opportunities are. So you have very fast response. And that safety switch that we saw there, the so-called electronic breaker, was capable of 3,000 zero crossings per, if you want to think of it as similar AC terms, 3,000 zero interrupts possible per second. So we didn't slip a decimal there. We're going from tens to hundreds to thousands, and I wouldn't be surprised if we end up with even faster switching over the next decade. So there's a lot going on there. Okay, I'm going to report. I'm going to shut down the polling. Any last people want to weigh in on the polling, and I'll give you the results. I think I just clicked end polling. Is that right, Greg? So I'm going to share the results. Let's see how that works. Are you all seeing the polling results? I'm not sure if you are. Somebody want to report back to me? Are you seeing the actual polling results?
Yes.
Yeah,
Okay.
Yep. The audience is.
So probably, as we should have suspected, most people are predicting that it will probably evolve to a hybrid system, both in terms of decentralization or what have you, distributed kind of activities. And same with AC/DC, that there's probably a little bit stronger group that's thinking that it's going to stay almost entirely AC or primarily AC. Whereas a centralized, it looks like there's relatively few people that would think they would stay primarily centralized. It will go to decentralized. So that's real interesting. I think that follows what we understand the market to be doing right now, is more and more people are looking at it. And of course, as I say, this is not a static issue. It's one that's constantly moving. The intersect of all these different technologies that are coming through, Internet of Things, power electronics, the electric car, the electric vehicles, cars, trucks, buses, et cetera, the killer app, as I call it, for power. I think if we go full on electric transportation, including air transport, which we know Elon and others are working on, we're likely to see, probably as much as a 40% increase in the amount of electricity just from those applications alone, on top of population growth and improving economies. So that's a real interesting results there. There were a lot of questions about, when is the things going to happen, and I would say that the likelihood of it moving faster and faster, we have to remember that most of these new technologies, particularly when you have converging technologies like we're seeing right now, where power electronics, electric vehicle, renewable energy, improvements in decentralization, et cetera, when they intersect simultaneously, that S-curve can get really steep. So you saw that for the AC grid to evolve over time roughly took, I'm going to say, 50 years. One would think that if there is a pretty big change involved going forward, although, the electrons don't know whether they're AC or DC, so they can just still travel through the same wires for the most part. And I know people are working on conversion kits for, so you don't have to rewire your house, that you could actually use the AC wiring to distribute DC and so on. But be that as it may, I think most people are predicting that if it is going to change, and most people, or more and more people are saying it will, that it's likely to take less than 2 decades, maybe even closer to 1 decade. And by the way, the shift from horse and carriage, and if you want to look up how long it took for some of this to happen, horse and carriage to automobiles only took 13 years for 80% change. So a lot going on there. I know we're out of time, and I apologize for those folks who have to leave us. Would like to invite you to stop into the eMERGE Alliance website and see all the committees that are working on the technical side. We mostly work on technical, what we call vanguard standards. We're trying to fill in the holes between some of the traditional organizations that are working on this, particularly with respect to microgrid systems. And want to invite you to the North American Smart Energy Week Conference and Exposition, which is in September, which will be in Anaheim. And stay tuned for if there's going to be any changes, but that's in September. And you can check into the website there at solarpowerinternational.com and see you can actually register now for that show. Thanks again to our sponsors, NorCal Controls, who does control systems, is both SCADA and DAS. Emeritas Technologies, I mentioned before, in this new block energy platform with DC distribution and a multi-layered of topologies. And last but not least is we have more webinars coming up. If you like this one, the next one is going to be on EV charging infrastructure for personal fleet and public transportation. We're going to talk more about hybrid appliances and use of microgrids in agriculture and other critical infrastructure, particularly as people talked about agriculture being somewhat critical in the case of a pandemic. And we'll talk about distributed intelligence a little bit, and also where microgrids are making it into other things all around. So thank you very much for attending. Hope you get a chance to check into the websites of our sponsors and the companies that presented today. And thank you very much. And we'll see you again soon at one of our webinars.